Hello everyone. Today we'll be dealing with the EMF equation of alternator, which is the continuation of model 5 synchronous generator. Let Z be the total number of stator conductors per phase. Stator conductors. So stator is a part of an alternator which is stationary. In that stator you have stator slots and you have stator conductors to be placed in that. P is the number of poles which is acting as a rotor. F is the frequency of the induced EMF in Hertz. Flux is the flux per pole in Weber. N represents the speed of the rotor in RPM. Now, what is the flux cut by the conductor in one revolution? That is, d phi is equal to p phi. How it is p phi? Let's see. So, as I said, the alternator has two parts, stator and rotor. Stator is represented by slots, and in these slots we are going to place the conductors. And the rotor is represented by poles. So as we are considering 4 poles here, north, and south. Let's assume when a single conductor cuts the flux of one pole. It can be any pole, it can be north, south. So if a single conductor cuts the flux of one pole, EMF is induced in that single conductor. So that is the EMF induced in one conductor by cutting the flux of one pole, or induced EMF per pole by one conductor. So as there are number of poles, therefore the flux cut by the conductor in one revolution is p phi. This p can be n number of poles, right? Next, time taken for one revolution. So what is the time taken for one revolution? It is dt is equal to 60 by n seconds. So how it is 60 by n? So as I said, what is the time taken to complete one revolution? So what is the time taken by the rotor to complete one full revolution? Right? In seconds we need to find. So n is represented as speed in RPM. If I want to represent that speed in RPS, rotation per second, it is n by 60. So here, time can be written as 1 by frequency. And also, we know that frequency of the induced EMF is given by F is equal to Pn by 120. Right? So here, the poles will remain constant. Even the number 120 will remain constant. Right? So only thing is that here frequency and the speed is going to vary. So if T is equal to 1 by F, then T can be also if F is replaced by N. So T can also be written as 1 by N. Now write what is N? It is N by 60. So you get 60 by N seconds. So that is the total time taken for one revolution in second is 60 by N second. Now, therefore, the average induced EMF in one conductor is given by d phi by dt. You have the value of d phi, that is p phi, dt is 60 by n. So we get p phi n by 60 volts as it is a induced EMF. So it is for only one conductor. Now what is the EMF induced per phase? So it is p phi n by 60 into z. Right? Now here we need to substitute the value of n as 120 F upon P, because we know that the frequency of the induced EMF is given by F is equal to Pn by 120. So here, if I replace N as 120 F upon P, keeping P phi Z as it is, so here P get cancels. This will get cancelled, this will become 2. So it is 2 F phi Z volts. So this is what you get after substituting N is equal to 120 F upon P by using this formula. So this is the induced EMF per phase. Now, what will be the form factor for a sinusoidal waveform? So it is E RMS by E average, which is equal to 1.11, which we have seen in model 2. Therefore, E RMS is equal to 1.11 into E average EMF induced per phase. So 1.11 into E average per phase is 1.11 into 2 into F phi Z. which is nothing but E RMS is equal to 2.22 F5Z volts. Therefore, the EMF equation of alternator is given by E phase is equal to 2.22 F5Z volts. Here, T is number of turns, which can be written as Z by 2. So, I can replace Z as 2T. Therefore, the equation will change to E phase is equal to 2.22 into F into 5 into 2T. So, the answer is 4.44 F5T volts. Right. Now, this is the end of the derivation. Right. Now, again, there are two more constant terms we need to write in this particular equation. That is nothing but Kp and Kd. Kp is pitch factor, which is given by cos beta by 2, and beta is the chording angle, which can be calculated by 180 degree by poles. Kd is distribution factor or the winding factor, which is calculated by sine of n alpha by 2 divided by n into sine alpha by 2, where the value of alpha can be calculated by slot angle, that is 180 by 3n. And n represents the number of slots per pole per phase. Z is the total number of conductors per phase, which can be calculated as slots into conductors per slot divided by phase. So, overall, after this derivation, you need to just write this equation. That is E phase 2.22 F5Z Kp into Kd volts, wherein we don't have the derivation on Kp Kd. It is just for the sake of problems, and these equations are very important in order to solve the problems. So in this chapter of synchronous generator, we have seen the introduction to the synchronous generator, construction of synchronous generator, that is the alternator, which is having stator and rotor. Again, rotor has two parts, salient pole and non-salient pole. The next topic was frequency of the induced EMF, and the third important topic is EMF equation of an alternator, which is again an important part which can be asked for more than 8 marks. Right? Now we'll be looking at few problems here. A 6-pole 3-phase star connected alternator has an armature with 98 slots and 12 conductors per slot. It revolves at 1000 rpm and the flux per pole is 0.5 Weber. Calculate the EMF generated if the winding factor is 0.97 and the conductors in each phase are in series. The coil is full pitched. So this is the equation. E phase is equal to 2.22 Kp Kd F 5Z. Here we have 90 slots, armature with 90 slots. So as I said, we have stator and rotor. Stator core is having slots. In these slots we are going to place the stator conductors. So the stator core is also called as armature core, and the stator slots are also called as armature slots, and the stator conductors are also called as armature conductors. So here this is the stator and we have slots, and these slots are nothing but 90 slots, and in each slot we have 12 conductors, that is 12 conductors per slot. Right? Fine. I think that is clear. So next, here in this we need to calculate Z, we need to calculate F, but here Kp and Kd value has been directly given in this problem. So if the winding factor is 0.97, so winding factor is nothing but your Kd, which is 0.97, and the coil is full pitched. If it is full pitched, the value of Kp becomes 1. Right? So we have 5 N slots, conductors per slots, poles, Kp and Kd. So we need to calculate Z. So how do we calculate Z? Z is what? Slots into conductors per slot per phase. So slots are how much? 90. Conductor per slots are 12. Per phase it is 3. So we get answer as 360. So it is easy to calculate frequency also. It is Pn by 120. Pa is 6, N is 1000, frequency is 120. So we get 50 Hz. So directly substitute the value of all Kp, Kd, F, 5Z, we get 19,380.6 volts. And if you want EL, which is a line voltage, which is equal to root 3 phase in star connected, as it is a 3-phase star connected alternator. So multiply root 3 into the phase value, we get 33,568.18 volts. Now there is one more problem wherein we don't have the value of, we don't have or mention the value of kp/kd, right? So here a 3-phase 16-pole alternator has a star connected winding with 144 slots. So there are 144 slots on the armature or on the stator, and there are 12 conductors per slot. In the sense, in each slot we have 10 conductors. Now what is the flux per pole? It is 30 milliweber. Right. Find E phase and E line. We need to find E phase and E line as it is a star connected. If the speed is 375. So this is my equation. So first I'll try to calculate Z. So Z is what? Slots into conductor per slot divided by 3. So how many slots are there? 144 slots. Into 10 conductors per slot, that is into 10 divided by 3 phase. So we get 480. So it is easy to calculate frequency also. It is Pn by 120. That is P is 16, N is 375 divided by 120. We get 50 Hertz. Now we need to calculate the value of Kp and Kd. So before that, we need to know what is N. N represents the number of slots per pole per phase. So what are the number of slots per pole per phase? Number of slots are 144 per pole. Pole are how many? 16 per phase. So this will be again divided. So it will be 144 divided by 16 into 3. So number of slots per pole per phase. We get 144 into 16 divided by 3. So that is, let's try to calculate. 144 divided by 16 into 3. We get answer as 3 only. Right. Now we need to calculate alpha, which is cording angle or the slot angle, we can say. 180 by 3n. So 180 by 3 into 3. 180 by 9, which gives me answer as 20. Similarly, I want to calculate beta. Beta is 180 by poles. So it is 180 by 16, which is nothing but 11.25. So here, first I'll try to calculate Kd. Kd formula is what? Sine of n alpha by 2 divided by n into sine of alpha by 2. So we have the value of n, which is 3. We have the value of alpha as 20. So sine of 3 into 20 divided by 2. 3 into sine of 20 by 2. We get answer as directly 9.959, 0.959. You just try to calculate, you will get the answer. Similarly, in order to calculate Kp, it is cos of beta by 2. So cos of beta by 2. So cos beta is how much? 11.25 by 2. So by the calculator we get the answer directly as, I'll just try to calculate here, cos of 11.25 divided by 2. We get 0.995. So this is how you have to calculate the value of Z, F, Kp and Kd. So here, if you know how to calculate the value of n, alpha and beta, so it is easy to calculate Kd and Kp. I just need to substitute the value of n, alpha and beta. So only consideration is that how do you calculate N? It is number of slots per pole per phase. Number of slots are 144, right? Again per phase it is, per pole it is, again per phase. So it is all divided. So you are just going to take 3 to the upper side. So it is 144 by 16 into 3, which gives me as 3. So straight away we are going to substitute the values of Kp, Kd in this. We get E phase is equal to 2.22, the value of Kp is 0.995, Kd value is 0.959, frequency is 50, flux is 30 milliweber per 30 milliweber, which is 30 into 10 to the minus 3, and the value of Z is 480. So let's try to calculate this. 2.22 into 0.995 into 0.959 into 50 into 30 into 10 raised to minus 3, it is, as it is milli, into 480. We get 1525.20 volts. So this is my E phase. So I need to calculate E line. It's √3 E phase. √3 into 1525.20. So √3 into 1525.20. I get the answer as 2641.72 volts. So this is how we are going to calculate the E phase and the E line voltage. So this is a problem where the first problem wherein we don't have the value of, we don't need to calculate the value of Kp and Kd, and the second problem where you need to calculate the value of Kp and Kd, right? So kindly go through the derivation and the problems. If you have any doubt, you can contact me. Thank you.